Thank you, Sylvia.
Well, Sylvia gave the game away when she talked to you about the year of the solar system. NASA has declared this. I believe that Mike Mogadhan did actually mention it at one of these meetings from what I could see in Astronauts. But, you know, it's meant to range from October 2010, which means we're well into it, through to August 2012. But they don't seem to have told anybody about this. It is actually on their website if you dig around for it. But they really haven't worked very hard on this. Now, personally, from my point of view, you may have gathered this, every year is Year of the Solar System. But what I want to do this year, I want that nevertheless we mark the year of the solar system. And so over the next 12-month period, I've got a number of presentations on the solar system up my sleeve. I think you'll like some of them. Hope you'll like all of them. And I wanted to start this time around with this one, the late shrinking moon. How likely is it? You know, just when you think you've heard it all, some scientific team comes up with yet another, I'm afraid, wacko idea to claim their 15 minutes in the limelight. Actually, I guess I should point over this way, should I? No, the wrong one.
That's the laser.
I'll get this right. There we go. Okay. Now, one of the more recent ones to catch my eye concerns the moon. Last August, there was an article published in the highly prestigious magazine, Science, which claimed that the moon, our moon, has shrunk at some time during the past 1 billion years. Now, when I read a scientific paper, I start by asking myself whether or not the fundamental premise of the paper makes scientific sense. If it doesn't, then I've got two choices. I can reject the paper from the outset, or I can continue reading in the expectation that the authors had better come up with some extraordinary evidence to support their extraordinary claims. So let's evaluate this late shrinking moon hypothesis against what we already know about solar system evolution. There we go. All right, now things shrink because they cool down, just like your telescope does at night as the night gets cooler, and so you have to adjust your focus as a consequence. So let's look at the heating and the cooling history of the moon. Now the solar system, as you now know, formed about 4.6 billion years ago, and the moon formed very shortly after that. The rocky planets and our rocky moon formed from the accretion of smaller particles and planetesimals, as they're called, whose motion, or kinetic energy, was transformed into heat. Now, in the case of the moon, we can still directly observe the relics of the magma ocean that formed by this heating, which progressively cooled and crystallized to form the white crust which we see today forming the Lunar Highlands. Now, these highlands are white because they're principally composed of the low-density, light-colored mineral plagioclase feldspar, which floated to the top of this magma ocean just like scum on a pond. Now, all this happened in the first 100 million years or so of solar system history. Next slide, please, Chris. Now, between 3.8 billion and about 3 billion years ago, that's billion with a B, the Great Bombardment left major impact scars on all the rocky planets and the moon, including the Great Mare basins that filled with dark lava that erupted from the lunar interior. Now, given that most of these lavas are significantly younger than the impact basins themselves, these lavas were not produced by the impacts, and this is key. How were they produced? Rather, they formed as radioactive isotopes of elements such as uranium, thorium, and potassium broke down radioactively to lead and argon over time, thereby releasing further heat to melt the interior of the moon. And these lavas ceased to erupt in great volumes shortly after 3 billion or so years ago, and certainly by about 2.5 billion years ago. And there's no evidence for volcanic eruptions whatsoever during the past 1 billion years. So what does all this tell us about the moon? It tells us that the first half of the moon's history involved at least 2 episodes of heating, melting, and cooling. But most importantly, it tells us that by the halfway mark in the moon's lifetime, the moon had already cooled significantly. Therefore, if the moon was going to shrink because of cooling, you might expect that it would have done so in middle age, around about 2.5 billion years ago, rather than in its golden years, less than 1 billion years ago. So should we now reject the late shrinking moon hypothesis on the basis that the premise is false? Not yet. So there is a way to salvage it. and it's based on things called phase changes with cooling. Phase change with cooling is simply a change in the way that the atoms of a given composition rearrange themselves in a submicroscopic volume of space as temperature decreases. Now remember, this is physical change. The chemical composition of the material remains the same. Next slide, please, Chris. Now you're all familiar with the phase change of water vapor, which is a gas phase, to water, which is a liquid phase, and then from water to ice, which is a solid phase. What happens during these phase changes from gas to solid is that the water molecules become more orderly in their arrangement, as you can see here. Next one, please, Chris. So what do you think happens to ice as it continues to cool to, say, minus 200 degrees Celsius? It shrinks as the water molecules rearrange themselves into tighter spatial arrangements. In other words, more mass in a smaller volume, which means a higher density. Well, the same thing can happen to minerals within a planetary body, except that the phase change there is also dependent on pressure. The simple example illustrated here, and it's a Mickey Mouse example, shows 8 atoms in a solid arranged at the corners of a submicroscopic cube, and that's on the left. With cooling, the atoms of the solid rearrange themselves such that a 9th atom is now stable at the center of the cube, and the cube now has a smaller volume and an increased density. Now, phase changes like this occur at specific temperatures and specific pressures. Can you think of an obvious example of phase changes like this that you know of from here on Earth?
Yeah, steel.
Huh?
Steel.
Steel. Every married woman in the audience should be able to give me the answer. Diamond. Diamonds. Graphite converts to diamond through a phase change at the specific temperature and pressures that exist at depths of about 150 kilometers beneath the Earth's surface. So it's conceivable that the moon could shrink quite late in its cooling history if a mineral phase change of the kind I've just shown you actually occurred deep in its interior sometime in the last 1 billion years. However, and this is the big however, we have no evidence for any such phase change within the moon at all, and certainly not during the last 1 billion years. Even if it has occurred, it would be an extraordinary event. And as the saying goes, extraordinary hypotheses require extraordinary evidence. So if you stuck with me this far, let's now look at the evidence that the science paper presented in favor of the late moon shrinkage. And don't worry, it's all about surface observations. But you would need a gigantic telescope to do them. Next slide, please, Chris. The evidence presented to support the late shrinking moon hypothesis in the paper comprises visual observations of these wiggly scarps on the moon's surface. Now, here's a typical example. What have I done with the pointer? There we go. Here's the typical example. There's the scarp. And I draw your attention to 2 points. Firstly, the distribution of shadows shows that the sun is shining from the left, and this scarp is a relatively steep slope facing to the right. Secondly, the impact craters in this image are very small pockmark features. Look at these things. They're tiny. That's the biggest thing. And so that tells us that even without a scale bar in this image, this scarp segment is not very long, nor is it very high. Now, what exactly do lunar scarps like this one actually represent? They certainly do represent a local shortening or contraction of the lunar surface. And this is a function of how they grow. The first diagram on the right shows you the undisturbed lunar surface. Hit it again, please, Chris. Next, a near horizontal fault, this thing down here. It forms at some unspecified depth, meters to kilometers, beneath the lunar surface, and then it ramps up. It ramps up towards the lunar surface. Next one, please, Chris. There's something, as yet unspecified, but I will specify at the end of the talk, pushes the rocks that sit on top of the fault to the right, as the red arrow here indicates, pushing them like this, up the ramp and then onto the lunar surface. So even for a very small shortening of the lunar surface, and that shortening is indicated by this green arrow here, in other words, that's the amount of shortening we're dealing with. We're going from there to that there. Even for a small amount of shortening, we now have an asymmetrical topographic high with a steep scarp facing in the direction of motion. Now, this kind of feature is very common on Earth, where we call them thrust faults. Now, let's take a look at some of the other examples of lunar scarps used as evidence in the science paper. Next one, please, Chris. Let's start with the Lee-Lincoln scarp in the southeastern corner of the Mare Serenitatis. This is the Mare Serenitatis here, and we're talking about somewhere down here. So where is this scarp? Well, here's the blow-up. This scarp is down here. There's that dashed line. That's the scarp itself there. And it's running between what are called the north and the south massifs. In other words, two hills, if you will, that bound a complicated-looking valley. This actually is the valley where Apollo 17, right there, that little white arrow, that's where Apollo 17 landed. Now, how big is this scarp? Next one, please, Chris. Well, here you can see scale bars, a scale bar in this image here, down there, which reads 1 kilometer. And that tells us that the scarp is pretty small and not that high. But I want you to notice how here you can actually see the trace of the scarp. It's wiggling. But notice how the northern part of the scarp here, it hugs the foot of the slope of this northern massif here. In other words, it hugs the foot of high ground. And remember this, because I'll come back to it in a minute. Next slide, please, Chris. Let's move to another scarp. This one's located on the far side this time, far side of the moon. The detailed image on the right, that's this here, that's this image here, is a blow-up of the southern part of the squiggly left-facing Mandelstam scarp in the other image. There's the scarp. And we've got this detail here is this entire image. Note the scale bars in both images. This is a pretty small feature. This scale bar down here is 3 kilometers. That one's 500 meters. The inset in the right-hand image, this one here, it shows a close-up of the scarp cutting across, right here, you can just see it, cutting across this small 20 to 40 meter across impact crater. You just see it cutting across there. Oh, and there's another cutoff actually right down there too on another one of these small craters. So we know, and this demonstrates that there has been some very minor movement. Next one, please, Chris. Now this is the Slipher scarp. This is the most spectacular scarp I could find among all the examples available on the web, and it's included in the science paper as well. The sun is shining from the left, and you have to admit that with its wiggles and its branches, it looks pretty impressive. By the way, this one's on the far side as well. Next slide, please, Chris. Trouble is, when you put it into context, within the Slipher crater, it's tiny. In fact, it's so small that I have to help you see where it is with this yellow arrow. And even with the yellow arrow, I still can't see the scarp itself. Okay, I'll come clean. This is the smallest scarp known, but the science paper did include it as evidence for a late shrinking moon. And by the way, there is a scale bar here. That's 20 kilometers. However, yet again, you notice how the scarp is close to high ground represented by the Slipher crater wall. Again, I'll come back to this in just a second. Next one, please, Chris. The words at the bottom are telling you what I'm trying to tell you here. You all know what this is. You've seen one, you've all seen one at some time or another, though hopefully not in your lunchbox. When an apple's interior shrinks, its surface wrinkles, or forms scarps, if you will, at several scales to accommodate this shrinkage. You don't need a PhD to see that there are lots of uniformly distributed small wrinkles, and it's uniform distribution that's the key thing. And there are a few large ones. I mean, these large ones here are pretty obvious, but look, it's wrinkled everywhere. So how does this compare with what we see on the moon? Next slide, please, Chris. Not so good. This is a map of the moon that places the near sides and the far sides in the same flat plane. Here's the near side, and this yellow stuff out here, and yellow and red out there, that's the far side being pulled around in this image. The black dots represent scarps that were already known before the science paper, and the white dots are the new scarps identified in the science paper. We've already seen that the scarps are not long, and here we see that their distribution is far from global and uniform. To be blunt, this looks nothing like our old dried-up apple of the previous slide. So from my perspective, things are not looking good for the late shrinking moon hypothesis, phase change or no phase change. Next one, please, Chris. So what do scarps look like on a rocky body that has really shrunk with decreasing temperature? You may remember several years ago, we discussed the scarps of Mercury. These are hundreds of kilometers in length, more than a kilometer high, and they're distributed all over the planetary surface. I don't have a scale bar on here, but these craters here, which are being cut by this scarp, these craters themselves are in the order of 20 to 40, at least, kilometers across. So we're in a different scale. Next one, please, Chris. And this image here of a single scarp on Mercury shows you just how big the shrinkage scarps of Mercury really are. Here's a part of Mercury. There's the horizon, give you an idea of what scale we're talking about. And this is one part of one scarp. Here's the scarp a little closer up. But you can see these are obviously a very different kettle of fish. Next one, please, Chris. So why does Mercury show such obvious surface evidence for internal shrinkage with cooling? Because as rocky planets go, frankly, it's weird. It has a disproportionately enormous metal core compared with standard planet formation theory, and still, despite MESSENGER, no one knows why. I'm hoping MESSENGER is actually going to give us a much better idea. But as the core cooled and shrank, it pulled the outer layers of the planet along with it and formed this amazing array of true shrinkage scarps, try saying that after a beer, that we see at the surface. Next one, please, Chris. So now you have all the evidence before you. Can you now answer the question I posed at the beginning of this talk? Have the authors of the science paper, yes, good. Have the authors of the science paper come up with some extraordinary evidence to support their extraordinary claim of a late shrinking moon? I would suggest that the answer is no. So now the onus is on me to explain their observations some other way. Fair enough. There's more than one way to feed a cat sour cream, and as a geologist, I know there's more than one way to create contraction or shortening features. It's all a question of scale. Let's go to the next slide, please, Chris. There we go. The moon is peppered with local topographic highs and lows. We just saw some of them. The outer parts of the topographic highs are commonly weak and they can slide, landslides. Remember how the lunar scarps are located fairly close to crater walls or to highland massifs? Material that slides down these topographic highs will tend to locally extend the lunar surface. Here, if this point here was originally up there and it's now slipped down, then I got that much local extension of the ground surface. But unless the moon is growing in size, something no one is suggesting here, nor have I heard anybody else suggest it, the lunar surface must locally contract or shorten somewhere else in order to accommodate this, as represented in this simplified diagram. So if this is sliding down slope here, and the material therefore bottoms out on this flat fault, which is below the surface, the white line is the old surface, and then ramps up the ramp here, then there is my shortening, represented by the green arrow, which is approximately the same as my local extension. Next one, please, Chris. So as you can see, I'm rejecting the late shrinking moon hypothesis because the fundamental premise the paper is based on makes no scientific sense. What do the authors have to say about the non-global distribution of their small scarps? Well, I quote, "Earlier populations of radial contraction probably resulted in other populations of small-scale thrust faults that are expected to be heavily degraded during and as yet unrecognized. Well, during the past 1 billion years, we're talking about micrometeorite bombardment, and I don't see how micrometeorite bombardment could efface an entire global array of these supposed shrinkage scarps. I have to tell you, this is one of the weakest scientific arguments I've seen in quite a while. I thank you for listening, and happy year of the solar system."
Questions? Thank you very much. Any questions? We have a few questions.
So I'd like to know if shrinkage was actually proven, would it destroy all our models of how the moon has affected the Earth?
No, because all we would have to be talking about a phase change. We know that within the Earth, for example, as the Earth has actually cooled over the 4.5 billion years of its life, we know that within the Earth, certain minerals which you might recognize, you might have seen in jewelers' stores, like garnet, for example, which is commonly used in costume jewelry. Garnet, as you go down into the Earth's interior, into the Earth's mantle, at around about 500-600 kilometers depth, it actually goes through a phase change and it shrinks. So it's only remarkable to actually be proposing something like this on the basis of the evidence I've shown you. If there was strong evidence that the moon had shrunk, and it was recent shrinkage, as in the last billion years, there are geological ways of accounting for it.
Does this affect your thoughts on Iapetus at all?
Does this?
Affect your thoughts on Iapetus?
Yes and no. We know that there are shrinkage fractures, shrinkage scarps on the icy moons in the outer solar system. And we also know that there are at least 4 different phases of ice, and they're all related to pressure, and they're all related to shrinkage. As you go from phase 1, 2, 3, and 4, you're getting denser and denser and denser ice. And so one would in fact expect that these outer moons made of ice, they have cooled over the last 4.5 billion years, and the reflection of that is the shrinkage cracks that we see on them. So, yes?
Go ahead. Hadley Rill near Apollo 15, is it a crack in the surface or a scarp, or what is it exactly?
Hadley Rill is actually a bit of a squiggle. It's not straight. It's not as squiggly as some of the rills that you see on the moon. The really squiggly ones, they're formed by erosion. They're actually formed by lava rivers. The Hadley Rill, though, in its location right out on the edge of the Mare Imbrium, is most likely related, in fact, to the dropping down of the floor of the Mare. Once this huge thickness, about 12 kilometers, of iron-rich basalt had actually filled the original impact basin. But it's a somewhat squiggly version of these gravity-driven fractures. Paul?
Simon, I was going to ask you, I'm experienced in metallurgy rather than in the other rock type of stuff. You know that in heat treating, you got ferrite, and you suddenly cool it, it becomes martensite. That is, it's a phase change.
Yep.
Is it possible that during the age of the solar system, the sun was cooler at certain times, thereby cooling the thing down and cooling the whole of the solar system down, causing this change of phase due to heat, thermal? It's a thermal thing.
Yeah, I do indeed. But what one's got to look at is where is the concentration of metals. The concentration of metals in all of the rocky planets is in the core. There are metals distributed through the mantle and through the crust, but the real concentration is in the core. And what we do know from the seismic experiments which were left by the Apollo astronauts on the moon, we know that the moon's core is extremely small. Its metal core is extremely small. So it may well be going through these kinds of phase changes, but it is so deep down and so small compared to the rocky part of the moon, it could not account for surface shrinkage, as opposed to Mercury with this huge metal core, which basically entrained the entire crust, or let me rephrase that, the rocky outer part of Mercury, because we don't actually know what it is, was entrained in the shrinkage of the metal core.
So it's heat treating, or whatever you want to call
Yeah.
it. It's
Yeah.
a thermal thing.
Yeah. Remember, though, martensite is very special. Martensite, of course, can retain a memory. And I'm not aware of martensite being found actually in the natural environment.
There's more up there.
Oh, yes.
Yeah, so just for context, I'm Stephen, I'm Sylvie's IT department. Anyway, after such a wonderful and meticulous defrocking, if you will, of such an interesting proposal or hypothesis, I'm left with 2 interesting questions. One is, how can a journal allow something so poorly supported to be published? And I think that might be a trend. And number 2 is, how does, I'm sure you're not the only one, or it's likely you're not the only one to come to these conclusions. How does the community as a whole actually challenge these types of things in journals and try to improve the science that we're seeing?
What you're talking about here is the fundamental flaw in the whole concept of the peer review system. The peer review system for scientific papers runs into one enormous problem. There aren't enough people who actually have the specialist knowledge to cover all the papers that are being submitted to journals. And so what happens is you'll get an astronomer with a physics background who's sent a paper like this to review and reviews it and says, well, it doesn't look bad to me, whereas it should have gone to a geologist, planetary geologist or otherwise. And this isn't the only example. I mean, in my own field of specialization, I have had to write entire papers actually challenging what has come out in other papers. You've got to be a little careful about how you do it. You don't want to be sort of attacking the people. You want to be attacking the ideas. On the other hand, if one is going to actually put in what is called a formal comment, that's the normal way of doing it in the peer-reviewed literature, then you actually have to be a member of that field of science. You already know the examples, for example, with respect to climate change, where any other scientist who isn't actually branded as a climatologist, basically, is basically challenged if they try to challenge any of the science that's put forward. So it's really, you're putting your finger on an inherent issue within the whole peer review system. But as Churchill said about democracy, it was a terrible system, but it was the best one he could think of. And peer review is the same thing. It has its flaws, and these kinds of things get through.
Thank you very much, Simon.
Thank you.